INQUA Congress 2023 in Rome, as you know. And the lecture will be given by Professor Ai Cheng, Institute of Global Environmental Change, Xi'an, Jiaotong University. Ai Cheng received his PhD degree in geochemistry at Nanjing University in 1988 and is currently a professor at Xi'an Jiaotong University. He has, over the past 3 decades, been at the leading edge in technical developments of U-series to address fundamental questions in quaternary climate change. He is one of the world leading experts on paleoclimate studies and played an important role in the reconstruction of climate history in numerous climate systems using Speleothem records worldwide. The related researches have produced a set of absolute chronological benchmarks for correlating and calibrating climate variability globally. The broad significance of his scientific contributions is attested by almost 600 publications, including 30 in Science and Nature, and the current ESI rank of 16th in geosciences. Ai Cheng is also a foreign corresponding member of Austrian Academy of Sciences, AGU Fellow, Geochemical Fellow of Geochemical Society, and AGU Emiliani Lecturer. So I am very happy to introduce Professor Ai Cheng. He will speak about Speleothem-based chronology and quaternary climate change. Please.
Thank you for your introduction. I also would like to thank all the organizers for giving me this great opportunity to report some of our results on Speleothem-based geochronology and quaternary climate change. So I think in our community, I mean quaternary science community, many people know Greenland ice core delta weighting record. Why? This is because the snow contains very important climate signal. For example, 18:0, 16:0 ratio. The snow accumulated on the polar region, including Greenland, and slowly turns to ice. If you drill ice core, measure the ice delta weighting, oxygen isotope ratios, you get like a ice core delta weighting record, such as very famous N-grip ice core delta weighting record. In low latitude, such as in monsoon regions, we don't have snow accumulation in general, but we have plenty of rainfall. The rainfall also contains very important climate signal, such as 18:0, 16:0 ratios. Most of the rainfall evaporates back to atmosphere or run off back to ocean, but a small portion of this rainfall get into cave system involving the formation of the stalagmite or speleism. So in this process, a tiny uranium as trace element dissolved from above soil or rocks get incorporated in the stalagmite. Another important thing is that the rainfall delta weighting signal got preserved in these stalagmite as well. So if you collect a stelagmite sample, and cut it to half, and polish it, and measure the carbonate, either a calcite or a aragonite, you get, this Speleothem data weighting record. This is a famous a record from a Hulu cave in Nanjing, which is my hometown. And actually, this the top panel is the stalagmite record. It's the new record, unpublished record. You can see it's compatible to the blue curve, which is the Angrip data weighting record. Both record record the data weighting of precipitation. So they are compatible, but notably, there's tiny difference here, is their timing scale. For the chronology of a cave record, or the Speleothem record, up panel, you see this absolute ages. At bottom, you see absolute ages. But people always think that's the same thing, but actually they are different in terms of their age bias, uncertainty, or the various, or this kind of a relative ages. Actually, if you deep understand this, there's some difference. It's not apparently looks like exactly same. The bottom, this age axis, top axis. This is very important. We should keep that in mind always. Okay. In technical side, in our university, for example, we have uranium-thorium dating method to get ages for samples less than 600,000 years old. And we have uranium-lead isotope dilution and laser ablation techniques to get ages for samples over 200,000 years. Plus, we also have a confocal microscope technique. We can get a very clear information or image to count the growth band, which is annual growth banding, to get relative ages. In addition, we have a bunch of facilities to get this we call them a proxy of hydroclimate conditions, such as delta 018, delta 17O. Currently, we can measure carbonate 17O as well. And the trace element, delta D, delta 018 from these isotope value from fluid inclusions, and the GDGTs from Speleothem samples. For this allows us to reconstruct the past this climate change, such as atmospheric circulation, humidity, rainfall, and the temperature. So in terms of uranium-thorium dating, this technique, persistently developed over more than half century. So currently, I think the improvement lies in isotope standard, gravimetric standard, high sensitivity instrumentation, uranium-234, thorium-230 half-lives, and particularly important is circular equilibrium standard. So pretty much this method reached its limit, upper limit, about 600,000 years. Beyond that, I'm not optimism you can push that in the near future to have any breakthrough in that aspect. I mean, the upper limit would be there for a while, at least in my point of view, at least 10 years. You won't want to improve that because of tons of reasons. Okay. But if you look at our for example, glacial, interglacial, this kind of variations over this long period of 2.6 million years Quaternary period. So the uranium-thorium dating only date the recent 600,000 years. But we don't have the method, we cannot use the uranium-thorium, this method to date sample over for the other 2 million years older than 600,000 years. So obviously, what are we going to do? The solution obviously is the uranium-lead method. Okay. So in about 25 years ago, some UK group, this is one of the early uranium-lead isotope dilution dating method. UK group, for example, David Richard, at that moment, he probably is a postdoc, I guess. Then he used the uranium-lead isotope dilution method to date this speleothem sample, this one, the cave deposit, and get an age about 248 plus minus 10,000 years, which is fairly good at 25 years ago. And soon after another 10 years, this is 15 years actually. It's I saw a abstract. They reported they're using laser ablation method to get the age from the same sample, which giving a age of 240 plus minus about 3,000 years. You can see that in terms of precision, it's slightly better, or like several-fold better. And after this abstract, in 2014, there is a paper dated some older cement of calcite cement, and that give you age is 158.8 plus minus 4.3. That's not 1,000 years. That's not. It's many years. It's far beyond the Quaternary. Okay. This method, I mean, the uranium-lead method, did yield a lot of very fantastic results. For example, I think this Oxford group dated the Speleothem growth period in Siberian caves before 400,000 years. They explained the relationship between an ice-free Arctic and permafrost thawing before 400,000 years. Another example is the work from a cave in this country, Italy. So the Morgan group established a very well-dated record between about 800,000 years and almost 1 million years, this great record. And what they found is that the obliquity seems very important or critical in triggering the ice age terminations during the Quaternary period. Okay, in our laboratory, we also developed the laser ablation and isotope dilution, these two methods, to dating samples over 200,000 years. So these three students are really talented students. They did a great job. They set up all these techniques in our laboratory. So challenge is remain. So the biggest challenge I can see right now is the correction. So one of the correction is about for the laser ablation method is sort of like a downhole effect, or most common is a matrix effect at central. And another type of correction, very critical for both isotope dilution and laser ablation, which is the initial correction. This initial is particularly critical for dating Quaternary speleothems. This is because it significantly changed the Concordia curve, which you can get, based on which you can get the your uranium-lead age. For example, here is our date. We date this sample, we get ice core and get the uncorrected age. It's 936 plus minus 3,000 years. In terms of precision, it's pretty good. It's 2 sigma. So, but we know this is just apparent, just a face value. Then after correction, and you see the corrected age is 514 plus minus 4. This is because it is initial uranium-234. Delta uranium-234 was really high. It's 2015, 150 per mil. It's really high. Therefore, the initial correction is so huge. It's a huge amount of correction. So we correct almost more than 400,000 years correction. Did we get this correction, feasible or right or properly? But here is a test. So the upper green curve is published sample delta weighting record. Around this time range is 640,000 to like 520,000 this time period. Then after correction, this bottom this panel show this Shui Xi cave. We call this Shui Xi cave. This is a recognized sample. We see that they compatible or duplicate the record we dated previously by uranium thorium method. This gives us greater confidence that we should be able to correct this properly. After correction, they both are matched really well. So another issue is about a standardization of laser ablation method. Currently, in our community, we have 3 common used standards for laser ablation method, but more or less, as I know, mostly a laboratory reported about a similar result from these 3, or consistent result from these 3 standards. Nevertheless, you can see that the youngest is about 3 million years, is already beyond the Quaternary time period. So none of them really a standard in the typical age range in the Quaternary time period. Therefore, we made another very good standard. This standard is from a sample cave. This is a pretty big chunk of stalagmite. So it has just about the right amount of distribution or amount of the common lead. Therefore, you could have some point around this region. And also, some portion is really clean. Therefore, you're going to have some dates very close to the Concordia, this line. So this is the advantage of this sample. Another advantage of this sample, we do have, isotope dilution dates, which matches, it's somewhere here, you match these, is double check. Therefore, the complicated, like a matrix effect, all those things might be not a big issue. Now, another good thing for this particular sample is that we have a measurable delta uranium-234, which is about 5 per mil here. And the uranium concentration is in reasonable range for easy to measure this sample using laser ablation method. Another advantage lies in the fact we really be able to tune delta weighting time series to insolation. So as we tested in the younger portion, there's always this delta weighting time series follow insolation. So we can turn this this delta weighting, this time series to this precession or insolation curve. Therefore, we could potentially we could have it is true age. We think probably a few 1,000 years this kind of uncertainty, probably 2,000 years this uncertainty. Okay, this is the standardization, and also we test some comparison. We have made some comparison between uranium thorium age and uranium lead age. So you can see that these, we can date some sample really young, like 70,000 years old. Then they're all consistent, after correction, they're all consistent with uranium thorium age. So that means this method is easy to apply and potentially could have great potential. Okay. And here is some progresses. First, I'm excited about, this is my lifetime first time I see some, a Chinese speleothem record beyond the uranium thorium dating this range, beyond like 650,000 years ago. Then we have a recognized sample cover this range. We have a calcite sample cover this range. Both replicate really well. So another progress is this speleothem, which cover a large temporal period, time period. It has like 9 precession cycles. So if you measure delta uranium-234, the measured value decreased by half from 12 to 6, and the measured age increased from top to bottom by about 200,000 years. Basically, it's about 9 precession cycles. So this axis is actually the distance. Okay. This is the first a record beyond the so-called MPT, the middle Pleistocene transition. Okay, then here is another progress we have, achieved. We characterize important events beyond the Quaternary. It's at about 3.3 million years. It's called M2 event. So here is the full picture. I'll just give you some idea what we now have. The blue color curves are unpublished data. The green curve is more or less published data. It's covered last 600,000 years based on uranium thorium dating, and the blue, of course, based on uranium lead dating. What are we going to do with this? So first, we need to know the factor. So when you look at all the archives across a large portion of the Quaternary, not that many actually. So mainly including marine ice core lake or this kind of Lurs record. So however, direct and precise dating these materials is rather difficult, currently almost impossible. For example, this is the very familiar, this is one of our cornerstone for our quaternary research, especially climate change. This delta weighting of thorium, you can see this long-term development in terms of this record itself is getting improved step by step. However, behind this record, the timing scale or the chronology is more or less still based on orbital twinning strategy, which was developed about a half century ago. Okay, for the ice core record, if you look at their chronology, they're based more or less on the orbital twinning strategy. And our Lurs record from China is very beautiful, but the chronology are also ultimately based on orbital twinning strategy. So basically, chronology of those long marine lake alert and ice core records are all based more or less on their orbital turning strategy. Everything correlates to everything. Is that good? Is that great? I'm not sure. Differently, the cave delta weighting records are suitable for absolute uranium and thorium dating, and now have become this strong fourth leg of the paleoclimate research after marine, Lars, and ice core record. Okay, so for example, because Speleothem records are absolutely dated and thus independent from insolation calculations, this allows us to explore the relationship between climate change and insolation without potential circular reasoning. So for example, we found that the last 7 conventional terminations occur during the rise lips of Northern Hemisphere summer insolation, separated by 4 or 5 precession cycles. So another important observation is that while everyone knows that there is a MPT, Middle Pleistocene transition, that means from a 40,000 cycle world transit to 100,000 cycle world, like glacial, interglacial cycles. So, but for our record, we don't see this transition at all, because the 20,000 cycles is occurred throughout the entire Quaternary. So this is sort of consistent with modeling work to some extent. The modeling work showed a dual nature of orbital hydroclimate cycles, such as precipitation cycles in high and low latitude. In low latitude, I mean 30 degrees north to 30 degrees south, this range. So you see they fill up with red color. Red color indicated 20,000 years cycles are dominant, but the blue color indicated those regions with 100,000 years cycles in terms of annual precipitation. Mainly, the low latitude is the region where global monsoon prevails. So monsoon dynamics are driven by differential, not absolutely glacial, interglacial temperature, which not change the differential too much. It's a global synchronous signal. However, the monsoon driven by differential, like northern and the southern hemisphere insolation difference and delta SST, and particularly land and the sea contrasting in terms of temperature and pressure. Okay, so this really modeling work consistent with our observation. In Northern Hemisphere, summer Asian monsoon follow Northern Hemisphere insolation, summer insolation. But Southern Hemisphere, this record follow these records from Tapache Cave, Brazil, follow Southern Hemisphere insolation, consistent with the dual world, this kind of modeling work. And another important thing here I would like to point out is that this observation is important for uranium thorium dating systematics. Why? It's because if our dating system offset, for example, half per mil, which is tiny, but progressively this offset will result in the like many thousand years offset in older time period. This actually this is not the case. Therefore, we are fairly sure that the uranium thorium dating systematics have really accurate within like half per mil. This has some important implication that because this kind of a young side of these samples will have like equivalent like decadal this accuracy guarantee here. So with this kind of advantage, therefore we can date those kind of, we call this GSSP or GAS. This is a stratotype very accurately. So the accuracy at this range is guaranteed. So, for example, the 4-point Ka event, this is the stratotype. Actually, this is a GSSP, officially GSSP. So this record left figure is have a, okay, really not that great. It has a large uncertainty. To solve this problem, we dated another 2 samples from the same cave, Marvelon cave, around the 4.2 Ka event. We see that the event around the 4,000 years remains significant, however, but not unusual. For a official GAS, the global axillary stratotype, we also improved this quite a bit. And plus, we also established another 2 8.2 Ka event or stratotype in Northern Hemisphere in Beijing, China, and the Southern Hemisphere in Madagascar. So these 2 records is exactly or strictly anti-phased, suggesting a southward shift of ITCZ. So behind this stratotype. And here is the detail about our new Beijing record. You can see that I call this a new generation of Speleothem record. This absolute age is dated really well. It's about 10 to 15 years uncertainty. So plus it has, those bending very clear, the image can tell you exactly relative ages. And plus the amplitude of delta weighting, this amplitude is so big, you never miss their structure. It's about 3 per mu. Okay, another very important event or stratotype is the end of young Dryas. Young Dryas is important not only for the GSSP, but also important as a last youngest Millennial scale event, which gave you smallest absolute dating uncertainty. So we date this sample collected by AMOC group from Spain. This is a critical sample. So now the end of the younger Dryas, the range is about 25 years uncertainty. This is comparable with Chinese Speleothem record now. Chinese Speleothem record is even better. It's about 10 years uncertainty at this range. Therefore, this the important things that is now we can compare with Angrip directly. So because this is calibrated by Spain record, therefore we really be able to link high latitude and the low latitude because the dating systematics is eventually the same dating systematics. Okay, so this is important because we can test our correlation strategy. For example, between Angrip and a Chinese record. So this is the bridge. So, and we found that breakpoint make more sense, or actually supposed to use breakpoint, not previous use the middle point correlation strategy. Okay, so this is consistent with the ice core record. You see their breakpoint correlation should be right here, not use the middle point correlation. That doesn't make sense because this the chronology is they're from the same cave, same core. Okay, so we also following the same strategy. We established a bunch of correlation strategy. We correlate major climate records together on the same chronology. Synchronize them. Okay. Now, in another research forefront, we now get a lot of high precision chronology benchmarks for correlating and calibrating climate variability. So our record is much better in terms of the uncertainty. It's 1 order of magnitude better than current used ice core chronology, which is GCC05. So those two aspects give us a really opportunity to put all the major climate record on same chronology, which precise chronology. This is sort of like paleoclimate Rosetta Stone. This Rosetta Stone is significant because from this stone we can see, for example, at the end of Heinrich Stadium, the strong South American monsoon change are always prior to the Greenland temperature jump and Asian monsoon termination. So, and another thing I would mention, is that this Rosetta Stone also going to tell you that the top panel, the green curve, as you already seen, is the Asian monsoon record. The red color curve is insolation. If you take the insolation, this is the orbital component, remove it out, then you get the gray curve, which I think represent or indicate the suborbital variability of Asian monsoon. What you can tell is that if you, because we have all this record on the same chronology, then we see a AMOC Asian monsoon. It is really close to coupled and not like a Greenland ice core. This is a new just freshwater hosting experiment. So you can see here is freshwater forcing and the stop. And then you can see the response from a North Atlantic SST and the sea ice coverage and as well as delta weighting of precipitation in Greenland, over Greenland. They seems on the same page, but in terms of the detailed timing and the structure, the AMOC and the Asian monsoon delta weighting record are coupled together. So this is this new experiment confirm our a conclusion that there is a really this kind of close coupling relationship. Okay, last slide, I would like to show you some ongoing work. For example, we are now working on this stegomite. This is something slightly shorter than might, about 150 centimeter tall. It has several precession cycles. Importantly, it crosses BM this paleomagnetic boundary. Therefore, we should be able to nail down this boundary in terms of their absolute time and their at where in the insolation curve. So this stegomite, probably some of you knew that they can measure paleomagnetic value. Therefore, you can figure out where exactly this transition occurred. So another thing one of my students is working on is that it seems there is a transition here, between Pliocene and the Quaternary in terms of delta weighting. This is a delta weighting from the same came. So there is a systematic change here, but he thought maybe Central American seaway closure may play some important role because they're going to intensify the AMOC. Okay. So finally, here is my summary. I would like to borrow a sentence from John Woodhead. He had a review paper on uranium-lead chronology of Speleothem 10 years ago. 2012, I think. What he said, concluded, is that the Speleothem chronometer appears to have a brighter future indeed. And I do agree. In my perspective, high resolution and absolute dated Speleothem record and their correlations with other climate records are emerging over the Quaternary, which will provide us a key to unlock various mysteries remain in Quaternary climate change. So I would like to thank you very much for your time.
Thank you very much for being here. It was a great honor for all of us. And to make you remember this talk and this event, I'll give you the replica of the original pin that was produced in the Congress of 1953, 70 years ago.
Thank you
so
much.
Please, thank you.
Okay, thank you very much again. And the plenary lecture is over. Now we move to the poster session. Thank you very much.